Okay. So let's talk about transforming your data. Yes. Okay. Sometimes we look down at the first thing you should always do is exploratory data. This should be something, we talked about that earlier in the course, always really just get a feel for your numbers. Get means and standard deviations and maybe a few graphs. You can just quickly draw on, even by hand. Doesn't matter how you do it. It's for your own edification, so you get a feel for your numbers. And usually, then the stats, you do the stats, it's like, oh, that's exactly what I thought. My graph looks like this, and I got a significant F. Yay. Right? My PhD supervisor, Sarah Shuttleworth, always said statistics are there to prove what you already know. You should have been looking at your data enough that you have a feel for it. You can look at it and say, oh, I see. I know what happened. Chickadees are like this and juncos are like this. He said it from personal experience. Okay. But sometimes you do the ANOVA and you get nothing. You don't get a significant F. And it's like, well, what happened? Most likely thing is a violation of an assumption. We talked about the other day about what would you be troubled at all by an F that's less than 1? And if it's a lot less, it shouldn't be possible. But if you violate an assumption pretty severely, you might get an F less than 1. But even if you violate an assumption severely, and you don't get an F less than 1, but you get a non-significant F, when you look at the data and go, come on, these are different. Right? The nice thing is, by the way, violating assumptions makes your test more conservative, not more liberal. You don't make false positives, but you miss stuff that's really there. You don't want that to happen. So the most common thing is that it's a violation of homogeneity of variance. It's almost always what it is. First of all, you're not going to violate independent observations because you did that with design. That's the first thing. Secondly, it's unlikely to be a problem with random sampling or the distribution of errors around the mean, because frankly, those don't hurt too much when you can violate the crap out of ANOVA with those assumptions. Homogeneity of variance you can violate to a point. But at some point, it breaks. Ooh, we're for transition today. So what can be done? Well, we can transform our data. Basically, we're going to do some sort of mathematical operation. We talked a lot earlier in the course about adding a constant to a distribution or multiplying times a constant. That's a transformation. Adding a constant's not going to do anything with your variances, so who cares? Multiplying by a constant will. So what you're going to do is some sort of mathematical operation on all the numbers. You can do it the same to all of them. You can't just say, oh, well, I'll just add 5 to all the low ones. That's called cheating. That's different. We're going to do the same thing to all of them. Some people will tell you that it's not fair, you can't do that, and it is fair. And it's fair because all you're doing is re-expressing units. All you're doing is re-expressing your units, right? You're just changing the units of measure. And we do this all the time. I know in the first assignment you guys had, remember to change the distribution, you were changing it from centimeters to inches or whatever, inches to centimeters, I can't remember, I don't care. As we live in a border city and we hear American with radio stations and TV stations that, we don't have TV stations, we're doing. They have TV stations across the river, but they don't come in on cable, so I don't want them. But on the radio you'll hear like the weather and they'll talk about the wind speed in miles per hour and kilometers per hour. They'll talk about the temperature in Celsius and in Fahrenheit. They'll do both. And they're both right. There's nothing wrong with Fahrenheit. There's nothing, it's perhaps a little intuitively not very pleasing that water boils at 212 degrees, but whatever. We should be using kelvins anyway. Real 0 point. Right? It's a cold one out there today. It's 253. That's funny. 2017 actually. But it would make it sound warm. It's cold out. It's but really cold would be 100. That's like cold like on Mars. So you just change the units. There's nothing wrong with doing. Okay. So it's not something that should scare you or anything like that, or you think like you're sort of cheating, because you're not. So the first we'll talk about is a log transformation. We're going to take the logarithm of a number. Do you know what logarithms are? Who doesn't know what a logarithm is? Put your hand up. I can teach you in 45 seconds. You don't remember? That's good. Okay, that's fine. At least you admitted it. Okay. I'm going to do log base 10 because it's easy. I can do it in my head. I can't do, well, I can do some log base 8, but not very many. So let's do log base 10. So the log of is 1. Log 10, what am I doing here? 100 is 2. That's 5. 10 to the 5th, right? 10 squared, 10 to the 1. That's all it is. Some of you, I just look at your face, I remember learning that in grade 10, but it went away. And now it's back. It's a logarithmic scale. We have logarithmic scales in psychology. Decibels are logarithmic scales, right? 70 decibels is 10 times louder than 60 decibels. Right? 130 decibels, which is right at the threshold of pain, is 10 times louder than 120 decibels, which is really, really loud. 140 decibels, which is working around jet engines, will actually perforate your eardrum. 130 just hurts a bit. 130, if you've been to a concert standing next to a PA, you've had 130. Right? 140, it actually, your ears explode. Like ear protection. That's why you see guys at the airport with ear protection. So what's that going to do? It's going to take down big numbers. Do you understand what logarithms are? Now you get it? You do log base 5, log base. You know, we actually don't hardly ever use log base 10. It's used sometimes, it's used in decibels, for example. If you look back, you took neuropharmacology with me, and I had that nice straight line between D2 binding efficiency and ED50 of antipsychotic drugs. It's actually a logarithmic scale. If you look closely at it. We use log scales. A lot of things in nature are logarithmic. It's just pretty common. Reaction time is logarithmic. Reaction time in fatigue, reaction time in alcohol drank. Goes straight up. But we can turn that into a straight line. That's all it does. It takes an exponential curve and turns it into a straight line. So this is going to pulls down big numbers way more than it pulls down small numbers. That's what it's going to do. So exponential curves like reaction times, as I just mentioned. So if you've got 4 groups of people and they're different amounts of alcohol drank, okay, and you're going to get a curve that looks like a graph that's like bang, 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 and the variances are going to be way bigger because the means are so much bigger, right? Oh, the problem is you can't take a logarithm of a negative number. That's an issue, okay? Or 0. The logarithm of 0 is undefined. It doesn't exist. So what you do, if you get something that's below 0, just add a constant to all the numbers. So let's say the lowest number you got is -5. Just add 10 to all of them, then take the logarithm. It's perfectly fine. Perfectly fine. So it's log of x plus k. You typically probably wouldn't use the log. You would use the what's called the ln, which is, if you've got a calculator, it'll say that, ln, which is just the log of the base of base e. E is a mathematical constant. It's kind of pi, except it's not pi, it's e. 2.71828 ish. And it's called natural logarithm because a lot of things in nature, just like, pi, important in nature, so is e. Okay? Questions? Okay? Make you look concerned. You got a question? Yes.
Yes. I was wondering, like when you're adding a constant, are you adding it so it's high enough to make the number a positive number?
Exactly.
Okay.
To make the lowest number a positive number. Yeah. Just as long as it's not 0. Yep. Anything else? Other questions on logarithms? See, you all learned it in high school and you thought it's never going to come up again. Ah! You're wrong. Okay. So you might do that with something that you look at the data and you go, wow. Does that. Goes way up. Probably a logarithmic transformation. Square root. I'm not even going to tell you why. But with counted data, so how many of? a lot of times you get a problem with counted data that you get the variance gets screwed up. So what you do is you take the square root. Why is that? It's because the means end up being proportional to the variances. With counted data, you oftentimes get, it's just one of those things, you end up with means that are proportional to the variances. What square roots do is they take care of that problem. You might add a constant first again, because like Christina said, you don't want negative numbers for your low sum. You can't take square roots of negative numbers, but you can. You get imaginary numbers, and that's not going to help anybody. So, did you know that square root of negative 1 is I, an imaginary number, which is used a lot in electronics, I guess, which is kind of cool. It's a pretend number, Christina.
Could you, would you do the log first and then
No.
add?
No.
You add first?
No, you would always add first if you wouldn't say a log or square root, because you can't take the logarithm of a number less than 0. It just can't be done. It's mathematically impossible. And you can't take the square root of a number less than 0. Right? You can, but you get imaginary numbers, and they're of no use to anybody except people that design circuits and physicists and stuff. Magic people, wizards. So add a constant. Again, nothing wrong with doing that. Reciprocal. Just flip the number over. Now, so the reciprocal of 5 is 1/5. Reciprocal of a half is 2. Reciprocal of 2/3 is 3 halves. Right? That's reciprocal. He's flipping the numerator and denominator. Makes the range smaller, so the variances get smaller. This is great with latencies. So if you got time, so you're looking at how long it takes a rat to run a maze, for example, or a person to complete a task. This may, in fact, Josh Havily's honors thesis, he's looking at latencies as one of the variables, and I imagine we're going to have to do this. And all it is, you're turning time, you're turning it into speed. If we said, how long does it take to drive to Sudbury? And I said 3.5 hours. If I just take that and flip it over, it's an estimate of speed, isn't it? Because remember, it's kilometers per hour, not hours per kilometer. Just flip it over. Just flipping it over. This works really well with latency. Just turning speed into, time into speed. It's really nothing magical. Arcsine, this gets weird. How many here remember their trigonometry? Don't worry, I'm curious. Do you teach that anymore? Yeah. Good. Good. It's cool. Trigonometry is actually really neat. It's like geometry. It's like analytical geometry. You know, like the angle sine angle theorem and all that stuff. I love that stuff. It's like a puzzle. That was neat math. You're all looking at me like there's something wrong with me, aren't you? Or it's more evidence thereof, I guess is the arcsine. Okay, this is with proportions. Proportions, percentages, that kind of thing. One of the problems with proportions, so it's more like if you got a score, on average in a group where most people are at 100%, there's not very much variance, or at 90%, there's not going to be much variance there. Or at 10%, not much variance there. But at 50%, just think about this intuitively, let's don't worry about it mathematically, but at 50%, it can be wildly all over the place. So scores in the middle have fatter variance than scores at the top or the bottom. We want something that leaves those small variances alone and sucks the one in the middle down to the size of those two small ones. Because think about it, if we've got an average of 90, so you get 90% correct. There's not very many people that got 10% in that group, or 50% in that group, or they mostly run around 90. What about 10% correct? No, they mostly run around 10. But around 50, you can be all over the place and just average out to 50. So you get this really fat variance in the middle, and these tiny little variances at the top. We got to do something about that. And the nice thing is Arcsine takes care of that. So it stretches out both tails to pull the middle flatter. It's actually, you don't just do the arcsine. You do 2 times the arcsine square root of the number. So you take the square root of the number, you multiply, you take the arcsine of the value to the square root of, and multiply it times 2. Because that works. So if the idea of sucking the whole thing out, pulling it like that, stretching it out to flatten out the middle makes some sense, that's good. If it doesn't, you are Catholic and I am Pope Dave the First. And I'm speaking on a matter of dogma. Nothing? No? I probably offend all the Catholics. I imagine the present Pope would like that job. He seems like an okay guy.
Dave.
Yep.
So are you stretching out all the numbers, or are you stretching out the percentages?
What you're basically doing is you have a distribution that looks like the distribution of scores. Of averages. You look something like this, okay? The thing is, you get the same number. That's a bad drawing. Actually, I shouldn't do it that way. Okay, these are variances. These aren't scores, but they all, okay? That's what I'm drawing here. The thing is, in the middle, yeah, actually, let's go with this. That's better. Okay, this is variance from there's the mean along that axis. These are where the scores are. There's the same number of scores within this weird shape that looks like lips at any given point. So you're going to see that you get a lot more variance in the middle than you get at the extremes. Does that make sense? Now what I want to do is I want to find something mathematically where I can just pull this over here and pull this way over here. So I get something that looks more like this. That's better. Now the variance is the same. And that's what this does. That's what that does. What? You okay? Okay. No, if you have a good way to say it. Does that make sense what I've said there? No? We're doing that. We're pulling it. Stretching it out. That's what 2 times the arcsine square root does. Maybe I'll take a picture of that. Put it on the blow up there because that might help. Okay. I've used that one. I've used that one before. And I remember a couple years ago, somebody's honors thesis, she came back to my office, and I wouldn't say she was crying, but she was very upset. Because it's like, this looked like it worked, and it didn't. Why didn't we get a significant F? And I said, oh, it's proportions. Yeah. Go do 2 times the arcsine square root transformation, it'll fix it. Mickey.
But how is that not, like, cheating? Yeah.
How's it not cheating?
Yeah, how's that not
How is Celsius okay and Fahrenheit okay?
I don't know how.
They're both the same. They're measuring the same thing, they're just using different scales.
Yeah.
Yeah, that's all this is.
But like you're manipulating the data.
No. I'm changing the way I measure. It's a difference. I'm changing the scale.
Okay.
I'm going from inches to centimeters. I'm going from Fahrenheit to Celsius.
Okay.
Yeah, that's all I'm doing here. Yeah, because like I said, if I said what we're going to do is we're just going to subtract numbers from the ones in the middle to suck it all down to this, that's cheating.
Right.
That's different. But yeah, I'm just re-expressing it. I'm just changing the units. Christina.
Could people that have data that has no effect still manipulate that?
Do you mean transform it like we're talking about here? Or do you mean like cheat?
Well, like, because data like naturally has variations.
Of course it has variation.
Even if it's not.
We like variance. Variance is our friend. Yeah.
So can someone do that to make their project look better?
Not. So you're saying it's almost like, can someone torture the data enough so they'll tell you anything? That kind of thing?
Yeah.
Not really. It's not the case that if something's not there, you're not going to find it. If something's there, this helps you find it. But it doesn't mean that, because all we're doing here is changing the units. It's all we've done. The thing we measured is still the same. Can this be used as a way to cheat? Is basically what you're asking, right? And no, not really. Not really. All this is doing is it's fixing a violation of the assumptions that I know. It's a very good question you're asking, because and I think Mickey was feeling the same way, a little bit uncomfortable about this, because it's like, it sounds like you're just playing with numbers until it works. It's not what you're doing. You're re-expressing them. Celsius and Fahrenheit, Canadian dollars and American dollars, right? Euros and pounds, right?
What if you change it, or like to go through the transformations and it still doesn't?
Then you'd found nothing. Oh yeah, then you found nothing. Tom, you had a question.
So can we not? So we can't really over-transform data then?
Well, I guess if you just kept changing, eventually they're all going to turn out to be 0 or something. I don't know if you did all of them.
So but when we're trying to look for something, we should really transform as much as we can. To see
No,
there.
that's not what you should do.
Okay.
You should try to find there are rules that I wouldn't say. Well, this next slide kind of answers it.
Okay.
Let's see if the slide answers it. If not, we can keep talking about this. When do you transform your data? You don't just always transform your data. It's like, I got numbers. Hey, let's add 17 to them and take the logarithm and then, I don't know, pee on them. See what happens. No, that's not going to work. I guess you could. I don't know why you do that, but you could. I don't know why I threw in the weird part about peeing on your data. I've had data that I felt like, I've had data I've lit on fire. Well, this experiment didn't work. Wasted 6 months of my life. Nothing there. Burned it. What are you gonna do? It's totally useless data. Yeah, I had it in my office for a couple of years. Why am I keeping this? It's just taking up space on pages. Throw it in the fireplace. So you don't always transform your data. Now, it's when the variances are messy, that's when you can often transform data and fix that violation of an assumption. This is a way these are all ways to fix violations of the homogeneity of variance assumption. That's what these things do. They are not magic. Right? And if something's not there, no matter how much you transform it, you're not going to get something. I've given you some rough guidelines to pick which transformation to use. You could also Google this. There's all kinds of nice sort of resources online, or a good advanced statistics textbook. We'll tell you. I don't think our book has stuff on this. I think I pulled this out of my master's and PhD year stats book. But it's stuff you should know. But basically, if it's latencies, you're going to probably do reciprocal. If it's reaction time, you do log. If it's proportions, 2 times the arcsine square root. But there are times, well, let me finish my point here. If your data don't violate assumptions, you don't transform the data. It means if the data don't violate the assumptions and you look at it and you got no effect, you've just got no effect. Your experiment didn't work. Move on. Maybe light your stuff on fire. Just move on. Have a career. Stop whining. Fix it. You always present untransformed data. You never present transformed data to people. You tell in the text and in your talk or something, you transform your data. But I don't know. I know if I say percentage of words were calm. If 100% is perfect, 0% is awful, 50% if we got yes or no, let's say it's recognition, it's chance. That's easy, I understand that. I don't know what 2 times the arcsine square root of 100 is. It doesn't make any sense to me. I literally don't know what it is. I guess you could probably present logarithmic transformed reaction times because it's so common. That's about it, though. Go ahead, yeah.
What does it mean when the variance is messy?
Messy, meaning that they aren't the same.
Oh.
They should be roughly the same. And messy, as a rule of thumb, is one's 4 times bigger than another. That's usually at the point where the math falls apart. Oh, okay.
Yeah, I figured out what I was gonna say. Okay, every time. So, is it every time that you don't find an effect? Does that mean
No.
you violated assumption?
No, because a lot of times you don't find an effect because there's nothing there. Yeah. But if you look at it, it's especially when you look at data and you go, I know this group is doing better than this group. Why the hell doesn't it show up? Let's say you have something like this. You do exploratory data analysis. You've made some graphs. Okay? So you've got a graph. Looks like this. Wow, that looks good. Yay, you need error bars, right? Uh-oh. That's bad. Now I know why there's no effect here. These all overlap with each other. But the means are different. Like, they're really different. But look at that. The means are proportional, or the variances are kind of proportional to the means. As the means get bigger, the variances get bigger. I don't know. Sounds to me like a job for square root man. What are his powers? You take the square root number anytime in his head. Excelsior! So, in this case, it'd be like, yeah. Now, on the other hand, if these variances were not so wildly different, so if we had 3 groups that were pretty different, oh no, that's not going to work. Didn't work. Done. Move on. Trying to experiment. Actually, that probably would work. I think the one on the left is probably different from the one on the right, but it's pretty close. Move on. Okay? So it's when you violated the homogeneity of variance assumption, that's when you transform data. But I'll tell you something. I had my PhD supervisor said to me with one of my experiments, it would have been experiment 7 of my PhD thesis. You can go read, it's hanging up on the outside. It's called Broadbeck and Shuttleworth, 2 of those experiments, 1995. 2 of those are from my PhD thesis. And she said, you should transform these. I said, why? And she said, isn't that what you do with proportions? I said, when you don't get effects and it looks like they're different, yes, but why should I do it now? It makes it more complicated. I got to explain it in the paper. And there's one thing I know more of than Sarah, and it's one thing, and it's statistics. And she said, okay. But that, I got lucky that it worked out that way, that I found the effect without having to transform it, because it's just easier to talk about. Because if I show these data at a conference and someone says, yeah, but the error bars all overlap, how the hell did you find significant difference? Oh, I transform. Oh, okay. Right. So it's not the case that you always transform your data, but it is something that you can do to fix a specific set of problems. All right? Okay, we're done.